So I'd like to introduce Koji Oyama from M3L, and he's going to be talking more about jitter, wander, and time lock. We've kind of got a little theme going on this afternoon, and he's going to be focusing on some of the work that they've been doing specifically on ST2110 streams. So take it away, Koji-san.
Good afternoon, everyone. My name is Koji Oyama from M3L Japan. I would like to explain jitter, wander, and time lock of ST2110 video streams today. So previous session, he said that zero latency does not exist. I want to say zero jitter and wander does not don't exist. So, oh. Okay, I would like to introduce a little bit more about my background. So I've been working for business development for over 10 years. I used to be a LSI engineer, targeting for the network and video applications. And M3L is a Japanese IP core design company founded in 1997, located in Kawasaki, suburb of Tokyo. And we have 10 employees, but almost employees are engineers, so even in our company present. And we have over 15 years experience with a professional video over IP technology. So this slide shows the objective and goal of this 30 minutes presentation. So hopefully this presentation help you know what happened inside your 2110 and the 2059 function boxes. So sometimes you feel the such boxes just as black boxes, but and a few people don't know they are. Few people know they are inside. So what happened inside? So please be interested in the inside the box. And so this presentation, first I will talk about the jitter and wander. So you can see the demo with sender video and receiver video. You can compare the two over video, so almost the same. But you don't know the what happened inside the box. So with the parameter and recovered clock. And so next, topic says I will talk about the time lock. So when you connect the optical cable to the 2110 network, and so you can see you can see the changes from the black screen to the video screen, and so you don't know the what happened inside the box. So I would like to explain these topics today. As this slide is just a reminder, so you know well about the SDI network and the IP-based network. So you know the SDI is you use a coax cable, and so it's good for the shorter distance rather than the IP-based network. The IP-based network is good for the longer distance and N2N connection, multiple point connection. And our key requirement is number of the so timing jitter is 2 unit intervals, less than the 2 unit intervals for the SDI. And other side, on the other side, so our for the IP network, so we have our requirement of the lock time, so within the 5 seconds. And this slide shows the so variation environment. So we are so the 3G and the 12G SDI video streams comes from the leader signal generator, and it comes from so it goes to the Xilinx FPGA board, and the board and have so our so IP cores, and it makes a 2110 packet from the SDI signal, and it output the 2110 packetized data to the other Xilinx evaluation board on right side. And so receiver board makes so the packetize the ST2110 packet, and it makes our recover the and then reproduce the SDI signal. And the reproduce the so SDI signal go to the so fabrics analyzer, and so we can measure the time jitter one there, and our jitter one there, and the lock time. And so fabrics box is input the black burst from the reader's box, and so it can be measure the so phase shift of the between the sender video and the received video. So you can so compare the how much different and how much so delay they have. And before I so showed you the result of the jitter one day and the lock time, so I just explained a little bit about but I will let you know the advanced information in order not to confuse you. The jitter and wonder I mentioned not PTP jitter and wonder. So I talk about the video, or so upper layer of the so 2110 and the 2059 layer. And jitter one day depends on each implementation. So the actual number is different from the equipment. But I believe that such number may be criteria for network system reliability. So if you can, measure the similar number of your equipment, you can see so how much reliability so your system has. So let's take a look at jitter and wonder. And jitter so jitter is our so short time variation of the synchronous instant of the digital signal, and wonder is so long time, so over the 1 second. And so this slide shows you the what is our 29 PTP synchronization for. So do you know what's the difference between the file-based transmission like YouTube and ST2110 plus 2059 transmission? The answer is so uh, target latency is much different. So 2110 and 2059 is a target for the low latency. And so you feel the so jitter and wonder is will be bad, but I think we need the jitter wonder to recover the clock so on the receiver side, because the so imagine that you can transmit the packet from the sender, and so how you how to reproduce the clock. It's a very I think it's a very difficult. Because it's data is transmitted by packet. So, uh, so the reason why I said to zero so zero jitter and one there don't exist. And so some jitter and one there are good for good to prevent resonance. So by feedback control. So this video is the fabrics display the 4K SD2110 over 25 gigabit transmission. So this is a video because the signal is very stable, so you can see just an image, but this is video. So you can so the output video is stable and no noise and no frame skip. But I plotted it to the timing jitter on this diagram. So this diagram, horizontal axis means the time, and the vertical axis means the timing jitter. And the color differences are different parameter of the PTP sync interval. And next diagram showed you the for the 3G SDI over 10 gig Ethernet, and maybe you can find the difference, but it's a little bit difficult to understand the difference. So I change the horizontal axis time to PTP interval, and I calculate the average of the timing jitter, and I plot it. So you can see the difference of the 3G SDI over 10G Ethernet and the 12G SDI over 25 gigabit Ethernet. It has about approximately four times different of the average timing jitter. But in fact, there's no difference between two, because the vertical axis uses the unit interval. Unit interval means cycle period of the clock period. So you know the 3G has a 4 times longer period of the 12G. So this average timing jitter is almost absolute value of the timing jitter is almost same. And next slide is for the one day. of the 12G SDI over 25 gigabit Ethernet, and so as I mentioned, I measure the phase shift of the sender video and the received video. So it has a latency, but you know that the uh, latency and the delay is slightly changing time by time. This means that vertical horizontal axis means that time. So you can it can change slightly and slowly changing. So and it this this is 0 and 10 seconds. So it has approximately 15 seconds cycle of the changes. So this is a wonder. And you can see this is for the 3G SDI over 10 gigabit Ethernet, and you can find the wonder easier than the previous one. And that's same as the previous example. I changed horizontal access time to PTP interval, and in order to we can find the difference of the each parameter, and then 3G lower PTP interval of the 3G SDI has also more wonder. So I summarize the Jitter and wonder result. So too few PTP interval can make Jitter and the wonder worse. And the default value of PTP interval, 8 hertz will be good. And it has 15 seconds period of phase shift between sending SDI and received SDI. So let's move on to the time lock. So I measure there different type of the two different type of the scenarios. One is in case of the connect the media node, equipment to the 2110 network. So and I measure I measure the number of the time lock time in scenario A, and for the scenario B is in case of the losing the grandmaster clock and reconnected it. And also I measure that as a lock time when losing the grandmasters. And this video is our lock time scenario A. And now our fiber cable connected, and you can see the video output. It means Ethernet linked, and the stat PTP locking, and now PTP locked. And then after that, okay, it takes a little bit time to become Jitter stable. And then now it rocked. Okay, so I plotted the PTP offset and phase shift and timing jitter on this diagram. So orange line means so timing jitter, and phase shift. Blue line means phase shift, and the PTP offset means yellow lines mean the so PTP offset, and you can see the it took 4.9 seconds to Ethernet linked, and it took 3.9 seconds to start PTP locking, and then it 4.5 seconds so PTP locked, and after that so it takes 12 after the 12 seconds so it became the jitter stable. Okay, so you can see there. So so sometimes talk about the PTP locked, but so the PTP locked does not mean the so jitter of the video audio clock is stable, because so video clock and the audio clock is stable at this point. And the next slide showed you the comparison of the 25G and the 10G. And so link time is so Ethernet link time is different, but so PTP lock time and jitter stable time is almost the same. And the next slide is so we are measured with the different parameter of the PTP sync interval. So upper diagram is so with the 2 Hz PTP interval, and lower diagram is with the 8 Hz PTP interval. So we can see the less PTP sync interval needs longer PTP lock and jitter stable time. Next video is so for the scenario B. Now Grandmaster lost, and then so Grandmaster reconnected, and after that, so PTP locking, and at the same time the PTP relocked and the jitter stable. It's a little bit so difficult to understand what's going on. So I brought this scenario on this diagram. So after the Grandmaster reconnected, in this case, so there's no error. These are 2110 system corrected PTP with correct PTP clock recovers clock with no error. And the next video shows you the in case of the error. So you don't know. We can see the no error. With the output video, but now GM lost and reconnected, and PTP locking. It's a little bit changed, much different from the previous case. So now we error detected. So video has no error, but the singular has error. And also, I plotted this value actual number on this diagram, and you can see the jitter error here, and yes, and one more example is we have no video, but in case of the jitter, it has a jitter error as well as the PTP errors, and you can see the how recover the clock. Okay, so I summarize the time lock result. So PTP lock it does not mean the jitter of jitter of video audio clock is stable, and jitter stable time for 10G and 12G are similar, and the less PTP sync interval needs longer PTP lock and jitter stable time. And for the when you lost the GM Grandmaster, there are three types of recovery three types of recovery. So without error and the jitter error, and both PTP and the jitter error you have. And conclusion. So you saw some example for jitter, one day, and the time lock, and hopefully you understand more about the 2110 and the 2059. And I highly recommend measuring the actual number of your own product, because it depends on the implementation. And so you know the 2059 and 2110 has so don't define such kind of the numbers at this moment. So I hope this presentation will help your work. Thank you.
Thank you, Koji. Do we have any questions? One question I had. Everybody knows that 2110 systems have jitter, but so do SDI systems. Especially not only do you have jitter in your signal, but you have jitter in your black burst, your clock. Mm-hmm. Do you see those as being equivalent, or is 2110 always going to be worse than SDI?
Yeah, but so when the signal is stable, the timing jitter is almost the same between the SDI and the 2110.
Okay.
But so lock time is different.
Yes,
so,
yes.
Yeah,
but lock time with SDI is pretty quick.
Yeah.
Yeah, but okay. No, I understand, but the long-term stable situation, you're in pretty good shape. Okay. Any other questions? All right. Thank you very much.
Thank you very much.